It's also my pleasure to introduce our IEEE Computer Society Seymour Cray Award winner, Satoshi Matsuoka.
Thanks, Bill. Thank you very much, Bill. And you know, the two wonderful talks, they're very hard acts to follow. First, I'd like to say that this Cray Award, I'm extremely honored, and also regard this as, you know, not just an award given to me, but it's given to a series of work that I had done, along with, you know, hundreds of, even thousands of colleagues, if you think of machines like Fugaku. So it's really an award given, you know, to the works, and you know, I'm just representing. You know, I myself is just representing the wonderful work that the teams have achieved. With that said, you know, Seymour Cray had always been my hero. You know, in my younger childhood days, my hero was Walter von Braun. You know, people in my age were like space age, and but instead of aspiring to be an astronaut, I really wanted to, you know, build rockets. And von Braun was my hero. Then after I discovered computing, you know, Seymour Cray had become my hero. You know, it was like, I didn't have exactly as a poster on my wall, but still, you know, he was like a father of supercomputing, and it was my aspiration that, you know, at least we have an expression in Japanese saying we'd at least be able to kind of, you know, be able to step on his shadows as a follower, of course, which is a very difficult goal to achieve. Seymour Cray, just like, you know, Thorsten came up with the idea of using quotes from Fernbach, and also came up with the same idea with Seymour Cray independently, so I'm not copying his tactics, mind you. But, you know, as Thorsten already expressed, Seymour had tons of quotes which became famous. Some which even became a meme, and you can find many of his quotes. You know, there are interviews on like videos, past videos. Also, lots of web pages that carry Seymour's past quotes. So, you know, in being awarded this prestigious award, I went back and looked at these quotes, and thought, you know, are we really living up to his expectations? That is HPC advancing in a way that he had perceived, or is it living up to his legacy? Have we progressed in a way that he had progressed in the field initially? And in some cases, it's even difficult for a genius like Seymour Cray to predict the future. And so we could go and review his quotes and really think about whether, you know, he got it right, he got it wrong, or, you know, he was kind of partially right, but there was some stuff that happened afterwards. So, you know, so that was my plan. And you know, instead of just giving my, you know, career talk, because I already had done that for SC14, my Fernbach talk. By the way, I'm wearing the same shirt as 2014, C14 here. So this was my plan, and I went back and looked at many of his quotes, and then see what happened. So the first time I attended SC was 1993. And Seymour was alive, so I could have met him, but I was just, you know, a young researcher starting out. So I had no privilege to actually meet him in person, unfortunately. But one of his quotes was like, you know, which Thorsten already expressed, was 1,024 chickens or ox. But one thing that really amazed me back in 1993 was he had built an ox. Which was many of you, the old timers, may recognize, was Cray 3. And Cray 3, to me, you know, when I first looked at it, it was just something out of science fiction. Yeah, you know, I won't go into the details of the architecture, but it was like cube-based, had all the chips already directly bonded, soldered onto the boards. And also because these were gamma arsenide chips, they had to be entirely submerged into fluoronaut in order to be able to cool them. And, you know, later on, I built this machine like Savame 3, which, you know, was a pretty good machine. But I try to post a picture so it kind of looks similar. But when you think of the coolness of the technology, the Cray, I'm still not stepping on its shadows yet, right? Because this is a much cooler machine. So, when we dig down and think about, okay, what were the technologies? Well, Cray 3 had like area SNR gate technology, had direct bonding, has CMOS, SRAM memory, immersive floor lock cooling. Whereas SPAMA 3, because we have built on more commodity technology, it's much more conventional. So you can say that Cray 3 back in 1993, when I first attended SC, in some ways, we could say may have had superior technology compared to what I had built in 2017. But what about performance? Well, when you think of the performance, I won't go into the details about what the flops, what the memory bandwidth is, what the power consumption rate was, and also power efficiency of the machine. But when you look at the numbers, it's about million, almost like a million times. SPAMA 3 is like a million times better. And you can extrapolate this to also Cray 3 versus Fugaku and A64FX. We can do the same comparison. And again, Cray 3, in terms of technology, you think it's more advanced. But it turns out when you do the comparison, this is the difference is almost like approaching a billion. It's like 10 to the 8th. And this one reason for this is, of course, as Thorsten already mentioned in his talk, that we were able to control the fleas. But when you look at it from the hardware perspective, the advances we had made in terms of the processor to processor is about 10 to the order of 3. One of the things, and that's enabled both by the advances in CMOS semiconductor manufacturing process, but we also able to exploit the parallelism, vector parallelism, and also the thread level parallelism that we were able to control because we have superior software and algorithms. And then we were able to, as this was part of Thorsten's talk, we were able to then scale that up to much bigger magnitude, like 10 to the 5th. And these combined allowed you to achieve this 10 to the 8th scaling from 1993 to 2027, where you achieve sort of an exascale-like performance. So the answer to this is, so we did achieve, on a per chip basis, 3 orders of magnitude speed up, and soon it'll be 10 to the 4th. But we also achieved immense scaling, being able to control the chickens or fleas or whatever you might call it. And this allowed us to also have even superior scaling. And these combined allowed us to scale well beyond. So Cray was somewhat right. You still need an ox. You need to improve on your processors. But also you need to control the increase on the parallelism. And combining both, that's how we are achieving 10 to the 8th and going beyond the speed up that he had achieved in 1993. So, so the next quote I was looking at is, okay, so the trouble with programmers is you can never tell what they're doing. And this is an antithesis of Jack's talk yesterday when he said, hardware people throw stuff over the fence, and the software people have to adapt to it. So this is a total mistrust on both sides, okay? So the hardware people don't trust the software people. Software people don't trust the hardware people. So that's bad. And so that's what we try to solve with the Fugaku project. When we started back in 2010, it took us 10 years. In 2021, we had the machine fully deployed, accepted, and in operation. Now, Fugaku is a very busy machine. So what did we do in these 10 years? Well, part of that is we tried to solve the problem of hardware people thinking that software people can't be trusted, and the software people thinking the hardware people can't be trusted. And that's called co-design. So we get together, we gather together in a single room and really think about how we improve the hardware in terms of software and algorithms, but improve the software in terms of the hardware that's being built. And and this started with what's called a post-K feasibility study, and it was actually me being more of a system and hardware and software systems and hardware guy, was actually leading the application team. And that's because the co-design really needed a system person to talk to the application people. So my partner, Hirofumi Tomita, who also works for me now at RIKEN, he's a climatologist. He's a real application guy. But we work together to basically corral together hundreds of application people into a single room and tell them, okay, you got to write a report saying what your algorithms are, what you need, and what you can do if we have achieved 2 orders of magnitude speed up in 10 years. What's the breakthrough size can you do? So, and this culminated into a report, which we compiled in 2014. I'm sorry about the artifact, the screen capture, which basically all the disciplines, pharmaceutical, medical, disaster, environment, things like material science, all the disciplines were basically supposed to, they had a template to fill. And they just filled up this, essentially these forms, telling them what's the current status, what the problem is for achieving speed up, and what are the opportunities, and what can be achieved if they do achieve such speed up. And also, they were asked to fill out this chart, which was a list of application, the algorithms, what are their bandwidth requirements, what are the flops requirements, what are the core algorithms that are driving the application. So this whole chart of what the discipline is actually using to drive their science. So, and then this was used to come up with 9 areas, and these were really, so the Fugaku was really designed as an application-first machine, covering these 9 areas as the target. Never LIMPAC machine, never any sort of benchmark machine, but the mission was to make these, not only to excel these applications faster, but to excel them fast enough such that there will be some breakthrough. There's some revolutionary breakthrough because there will be some qualitative change because of the quantitative speed up achieved with the new machine. And then this also, the design team was tasked, once we have these, how to achieve, and the targets are obviously very hard because, it involves scaling to the extreme. There were power difficulties, so achieving performance would be hard enough, but also had to be extremely power efficient, had to be very, very easy to use. And I won't really go into the details of how this co-design had been achieved because it's documented in several publications that we have made. But basically, throughout the process of system optimization, the co-design was still continued on the development process, but also the reciprocal was done. So because the design teams were given the details of some of the details of the early hardware, they improved their algorithms to comply with the new hardware changes and vice versa. So this continued, this ping pong persisted for the duration of the development that allows to come up with both not only the machine, but also the application that was ready to be deployed in the machine at the same time. And this allowed us to achieve the goal of having something like almost 2 orders of magnitude speed up across the various disciplines that span across the, mostly a lot of the important scientific areas that involve some sustainability goals. So the average speed up we got was about factor 70, but these are, again, these are not benchmark results. These are results emanating from real applications. And of course, we got benchmark. But we got the benchmark as a consolation and Gordon Bells and so forth. But that's one of the reasons how Fugaku succeeded. So, yeah, so I think we learned from, we tried to learn from Seymour's quotes, but we tried to correct this mistrust between the applications and the hardware design. The next quote is, well, the parity is for farmers. Or, so that was, so Jack's talk yesterday has some, one of the sections of Jack's talk, if you were paying attention, was saying the CDC 7600 crashes every 2 or 3 times a day. That was a single processor. So if you had 160,000 processors like Fugaku, if one crashed every few hours, you're not going to get anything done. So So actually, a lot of technological advances were made in these large-scale machines are not very trivial in that, well, so Torsten already talked about networks, but also things like resiliency, power, et cetera. All these technologies were very pertinent to achieving extreme scaling. And then there's no underestimation of the fact that this has been achieved both at hardware and also at the software level. So for example, Fujitsu A64FX is a very, very, very reliable processor. The reason is, well, Fujitsu's been making a mainframe for, decades. So what they have done is to not take, some commodity processor and shrink it and make it into a supercomputing chip. They put every RAS features they can think of out of their mainframe technology into the chip. So that allowed extreme resiliency or reliability. And of course, we couple this with other more software reliability techniques like checkpointing and so forth. But we have this fundamental basis by which the reliability is already there. So if you look at Fugaku's data center, there are no hardware maintenance people walking around. So I give tours on Fugaku every once and often, but there's nobody. The reason is, one of the reasons there's nobody is the machine really doesn't have to be maintained all that often because things don't break. And this kind of reliability is very important when you have jobs that typical Fugaku job at like thousands of nodes. Also, power is important, and Fugaku, the reason we can sustain a machine of 160,000 nodes is the fact that the power consumption is low. Now we have synthetics benchmark Green 500, but that doesn't tell the whole story. It's really the production, what the power consumption you have in production that's important. And because of the power crisis we are suffering due to the various global conditions in the world, which I will not go into detail, but we all know, we are having to go to extremes in terms of power savings and make the machine as efficient as possible. So right now, the average power on the Fugaku node is about 100 watts for about 2 watts per core, which is really low. If you ever built these machines, usually you think a node is like 300 watts, 400 watts. Fugaku is only 100 watts per node, and this is fairly consistent. And you can look at this web page, and you can find out for yourself. So this is like 1/3 to 1/4 compared to typical like server-grade CPU nodes built out of server-grade CPUs repurposed for HPC. So that's how we achieve this. That's how we achieve scalability, because otherwise, unless you achieve these extreme power efficiency, you can't pay electricity bills. And of course, interconnects as well. So Torsten already talked about the importance of interconnect. Well, Fugaku has 160,000 nodes, but how does it scale to 160,000 nodes? Well, because obviously we have a network that scales to 160,000 nodes. And when we built it, it's like very much like BlueGene, but we have not only the interconnect, the PHYs, and et cetera on the chip, but also the switch on the chip. So the Fugaku is a 160,000 node system, but has 160,000 node 10-port switches, because every Fugaku CPU has an embedded Tofu switch. And this not only gives us the scalability to 160,000, but also the power consumption of the network, including the AOCs and so forth, is about 8 to 9 watts. So when you have a 100-watt node, you cannot have a network that consumes 30 watts. Right? The network can, so you want the network to consume maybe like 10%, including its switches, to consume about 10% of the overall machine portfolio. So the network has to be really, really low power. Again, this is like 1/3 the power that you may see typically in things like InfiniBand or Slingshot. So all these combined allows you to have a supercomputer that people could buy. So farmers, later on Seymour Cray, farmers buy a lot of computers. So if you build something good for a farmer, it's good for everyone. Okay. So the final part of my talk. Like I said, anyone can build a fast CPU, but the trick is to build a fast system. And we're now embarked on this new studies to construct a new machine. Fugaku next to be deployed maybe in 2029. So what would be the important factor? Well, so it's really, a lot of, as Torsten said, really think of like being flop-centric, and that's really being very chip-centric. Think about what's the flops of this, what these particular chip like CPU or GPU provide. But that's a very wrong way of thinking about things. You really got to have system view. So what's a system view? Well, we really got to analyze what are we really computing, and what are the characteristics of the stuff, of the algorithms that we're computing. Of course, we go into much more detailed analysis with respect to the complexity of the compute versus data motion, as that Torsten has described. But to simplify things, I'll just say there are three types of kernels. There are compute-bound kernels, like the top 500. There are like bandwidth-bound kernels or memory-bound, which are memory or network-bound, like the HPCG. And then there are like latency-bound kernels, like the Graph 500. And in the past, when we have been building machines, like the specialized machines like the Cray 3 we have seen, kind of covered most of bandwidth bound because they were very, very memory-rich machines. And also, it has some compute, so the classic vector machines sort of covered this spectrum. They were not very good latency-bound machines. But then the commodity clusters, the cost CPU came about, and then we learned to parallelize applications using things like MPI and so forth. That allows us, and by the sheer numbers, allowed us to cover all three types of workloads. And then the GPUs came about, and the GPUs are sort of resurrections of the old classic vector machines. So we've discovered, people like, so I worked on it, many other people have worked on it. We can do even further speed up by recovering the region that was covered by the classic vector machines, taking that over from CPUs. Then we can build a much better machine. So that's how most of the GPU machines are built today, and that's how the workloads are divided. A lot of the compute-bound and bandwidth-bound workloads are on the GPU, but the latency-bound is on the CPU. And then we have a machine like Fugaku, which we might think is a resurrection of the CPU base, but actually it's not. We learned a lesson from GPU. We try to embed the vector processing units into the cores, much like the old vector machines have been doing. But then being a CPU, it also covered latency bound. So trying to combine the properties of GPU back into a CPU. But this tells us that we can think of various other types of combinations where we can have different types of processors or cores that could be covering different regions of these compute kernels. And then think of an architecture that would be covering these in a much more effective way compared to the machines we have today. So that's some of the studies we're doing. But then the question is, so given those three kernels, which ones are more dominant? Are compute-bound kernels dominant, or the bandwidth-bound kernels dominant? And we had for a long time suspected, and as Jack was saying, LIMPAC was being less and less representative of the typical workloads. But you think, is that true? And why is that, or is that true? So we went out and tried to look at across many applications, some ECP benchmarks, some RIKEN benchmarks, spec-OMP, or across various types of applications, and try to discover whether the compute-bound kernels really exist. Compute-bound being like GEM, level 3 BLAS, GEM-based kernels. And turns out, we just didn't detect the calls to the level 3 BLAS, but rather we basically cloud source student slaves, student workers, and then we had red teams and blue teams, and they try to manually go over the code and detect these patterns as well. So we use natural intelligence to discover these. And turns out that there are very little, almost no applications had these numerically intense kernels. So then we went and looked at the workloads of these machines, like K and Argonne, and also try to predict some of the future workloads involving more AI. So, and what's the speed up can achieve? So this is a system level view by, let's say, by having infinitely fast matrix kernel. So we have a top 100, you'll be number one because you're infinitely fast on matrix multiply. So then if you have a machine like that, what's going to be your speed up? Well, it turns out it's only like 7% speed up for the K computer. Okay, and 10% for an Argonne workloads. Maybe 30% for more machine, for like machine learning type workloads. So, and again, that's the reason is because most of the workloads we see today on supercomputers are on the left-hand side of the of this Louvre-line curve. They're bandwidth bound. So the only way of increasing system performance is mostly by increasing the bandwidth in the system, and not just the network bandwidth, the memory bandwidth. Really focus on data movement from flops to bytes, and this is exactly the same message I'm sending as Thorsten had been sending. So we have been doing a series of work, like looking at what kind of speed it can achieve by exploiting local memory. We have several papers about these theoretical, more or less some strawman architectures with a lot more, 10 times, 20 times the bandwidth using, things like SRAM stacking, and looking at various and running simulations to see how much speed up we can gain for various kernels. And also looking at how we can extend this to bigger systems. And it turns out that I won't go into details, but due to the various governing laws of speed up, the Amdahl's law versus Gustafson's law, we really need to have a homogeneous system, not heterogeneous system across the board, unlike many believe that we're going to much more heterogeneous systems. So I have to skip some of the contents, and I'm sorry, due to interest in time, and Bill is looking over me. But right now, so we embark on a journey looking from this algorithms, a system-wide view of what kind, and then coming back and saying what kind of processor do we need, or what kind of memory system do we need, what kind of interconnect do we need. And this is just a straw man we're showing to various people, and of course we're into much deeper conversation with the various vendors and chip designers and so forth. But we're trying to bring on various more innovations onto the table such that we can still continue to drive the performance forward even well beyond what we know with Fugaku and Frontier and these great machines we have now. So final slide. So what Cray said was, do things a little differently. And that's, not do what other people do. Don't follow the hype, let's say. And that will give you the maximum reward. And that's exactly, I think that's what we have been doing for the past, we have been doing for the past years. And moving forward, by not believing in a hype, like, this tremendous ultra teraflops processor, or ultra heterogeneous stuff, but looking at the principles, looking at where the bottlenecks are, and then thinking about what revolution technologies we can apply to build these future systems, I think will give us a maximum value return for the buck. And that's what to listen. We're learning a lot from Seymour Cray, and hope we are living up to his legends. Thank you.
Thank you, Satoshi. I think we could take one question. Is there a question? Yes, there.
Hi, congratulations for the award.
Thank you.
My name is Diego Roa from Argonne National Laboratories, University of Delaware, Capsule Lab. My question is, do you think we will see more hardware-level support for synchronization and communication across nodes?
Oh. Yeah, the question is, will there be additional synchronization features across the nodes? Yeah, that's something we are currently considering right now. And these kind of features have been in proposals since the days of like data flow days and eons ago, which we all kind of remember. Most of these synchronization, except for the hardware barriers, for global reduction, most of these mechanisms have so far proven to be not very useful. That said, one thing I had to kind of skip over is the fact that we need to strong scale. Because the limitation of the hardware, we need to start really thinking about strong scaling. And strong scaling would require various tactics, including having better localized synchronization. So by this requirement, it may be that we may have to start investing in some local synchronization techniques, but that's something that we're still considering, and there's nothing definite yet. Yeah, very good question. Thank you.
Thank you.
Right. Thank you. Thank you for attending this session. The session is now over. Enjoy your break.